It is difficult for us humans to fully comprehend the enormity of space. We are comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course Earth. But out there, over 18 billion kilometers, away from the Sun and beyond the heliopause, is the cold oblivion of interstellar space. The two Voyager probes are the only man-made objects ever to cross this threshold to this day. And until recently, only two known objects had ever made the opposite journey, passing from interstellar space into the solar system. These were the famous Oumuamua in 2017 and Borisov in 2019, which brought with them the thrill and perhaps even fear of being visited by something from the depths of space that humans cannot hope to reach in our lifetimes. In the 6 years since these visits, we had been enjoying some respite. But a recent observation has forced us to sit up and pay attention once more. Join me in this video as we explore all there is to know about NASA's latest observations of Comet 3I Atlas, the third interstellar object ever observed, which will make its closest approach to our Sun before the year is out. 3I Atlas has had a few different names in the short time we have been aware of it. But recent revelations about where this object came from and where it is heading turned this otherwise indistinguishable space rock into something worth taking note of. On the 1st of July this year, the NASA-funded Atlas Survey Telescope was performing its usual task of scanning the skies above for moving objects. The Atlas Projector, Asteroid Terrestrial Impact. Last alert system consists of 4 telescopes across Chile, South Africa, and Hawaii. These telescopes each take around 800 images every night and day. At the time of writing, they have registered 1,212 near-Earth objects that will pass within 3 astronomical units of our planet at perihelion. But on this particular night, the telescope in Rio Hurtado, Chile, reported some news-worthy observations. The Atlas telescopes are rather unique for their ability to survey the galactic plane, the bright disk-shaped region of our galaxy where most of its mass lies. See, other surveys like Pan-STARRS and the Catalina Sky Survey are often too sensitive to photograph this area without facing overexposure, so they tend to avoid it altogether. From the direction of the Sagittarius constellation, the Atlas telescope took 4 30-second survey images and found an object that was making a bayline towards our solar system. The object was initially named A11PL3 and quickly caught the attention of the Minor Planet Center MPC in Cambridge, Massachusetts. As the designated authority in charge of labeling and tracking minor bodies in the solar system, the MPC quickly put out an electronic circular about this new visitor, detailing all of its previous observations and providing information about its trajectory. In doing so, astronomers realized that, in fact, this object was no stranger to us. As it turned out, the Zwicky Transient Facility in California and the 3 other Atlas telescopes had all made pre-discovery observations of this object dating back as far as June 14th. With all of this data, the MPC deduced that the object has a hyperbolic and highly eccentric orbit, so much so that it had originated from interstellar space. This realization earned the object the name of 3I Atlas, as it is the third interstellar object to infiltrate our solar system. At first, the MPC could not be certain whether this object was an asteroid or a comet until the combined data revealed that it had a coma, a diffuse halo of dust and gas produced when ice is exposed to solar radiation and sublimates. This feature is far more typical of comets, which gave this object yet another name. C 2025. N1. The MPC has called for additional observations of this comet to help constrain its trajectory, so we can expect a flurry of new data in the upcoming months. And astronomers are naturally very excited. Michelle Bannister, an astronomer at the University of Canterbury in New Zealand, explained that working on the 2 previous visits from interstellar objects were transformational opportunities science-wise, so it is likely that this visitor will encourage the same. But what do we know already about this latest interstellar visitor? And what do scientists hope it can teach us in the near future? Firstly, do not worry, because this comet will pose no threat to Earth. At its closest approach to our planet, it will still be around 1.6 astronomical units away, that is over 600 times further than the Moon is from Earth. So since we are able to watch from a safe distance, what kind of journey will this comet take? As I mentioned earlier, 3I Atlas has a highly eccentric orbit currently, measuring at a value of around 6. For reference, an eccentricity of 0 represents a perfect circle, and anything above 1 is great enough for the object to escape the gravitational pull of the body it is orbiting and move more freely through space. So with an eccentricity of 6, this comet has one of the most extreme hyperbolic orbits yet measured, which may explain how it is able to travel so far through space to reach us. What is more surprising is the speed with which this comet is traveling. Its current incoming velocity is a rapid 58 kilometers per second. That is like running the length of 580 football pitches every second. This breakneck speed makes 3I Atlas the fastest traveling interstellar comet we have ever seen. Oumuamua and Borisov had velocities of just 26 and 32 kilometers per second respectively, resulting from their differently shaped orbits. With such a rapid approach, astronomers were keen to work out exactly where 3I Atlas was headed. The current orbit is heliocentric, or centered around our Sun, meaning that it's possible for astronomers to infer its incoming trajectory before it reaches us. On its closest approach to the Sun, on the 30th of October, the comet will be at a distance of 1.4 astronomical units, placing it just inside the orbit of Mars. In this graph of the comet's orbit, you can see the asymptotic shape of its approach as it veers past Mars and shoots back out into space. As the graph shows, I Atlas will not pass as close to the Sun as the famous Oumuamua did in 2017, and will follow a trajectory more similar to Borisov's. Once the interstellar nature of this comet was clear, astronomers employed the use of other globally distributed telescopes to better understand it. In particular, the telescopes from Las Cumbres Observatory LCO are purpose-built to observe transient astronomical events, which can include events like comet outbursts and other changes in brightness, using 36 Metra LCO telescopes based in Hawaii. Astronomers scheduled a 1-hour observation sequence for 3I Atlas. Their goal was to identify a light curve for the comet and to see whether it exhibited any rotational variability. Rotational variability means any kind of variation in brightness caused by the comet spinning on its rotational axis. Maybe it has an irregular shape and reflects light differently across its surface, or it has active regions that appear brighter to us when they face towards Earth. But by monitoring the changes in brightness over time, astronomers can identify repeating patterns which show that the comet has completed one cycle of rotation. Using the LCO telescopes, astronomers identified that the comet has a rotation period of around 29 hours, though, like much of the information about 3I Atlas, further observations are needed to constrain this. In a surprise to astronomers, 3I Atlas had a much flatter light curve than Oumuamua and exhibited only 0.2 magnitude of brightness variation throughout the 29-hour period. But despite this minimal variation in brightness, 3I Atlas is bright. In fact, it is the brightest interstellar object we have seen. Yet the comet was pretty faint right up until the end of May this year, when it reached a magnitude of around 20. But between then and the comet's discovery by Atlas, it has promptly increased to between 17.7 and 17.8 magnitude in the Atlas O band, which records light wavelengths between 560 and 820 nanometers. Not only is the comet bright, but it is large. From assumed albedo values, the diameter of its nucleus estimated at 10 kilometers. This makes it an order of magnitude larger than Oumuamua and even larger than Borisov, which measured between 1 and 2 kilometers in diameter. Further observations have also revealed that 3I Atlas shows faint levels of activity. As I mentioned, the comet has a marginal coma, which constitutes the fuzzy glowing halo of dust and gas that is produced when cometary ice sublimates upon exposure to the sun. You can make it out in the center of this image as a diffuse circle around the nucleus. The image is tracking the moving comet, which is why the surrounding stars appear blurred. But as well as a coma, 3I Atlas shows a tail. The MPC reported a tail spanning 3 arcseconds across the sky at an angle of around 280 degrees. This is pretty short, so the tail is often lost among the coma in images of the comet. As with many modern scientific discoveries, the advances in technology and communication mean that people around the world can get in on the excitement, and that is exactly what is happening for 3I Atlas. Amateur astronomers and experts alike are contributing their own observations of the comet, so our state of knowledge is constantly being updated. For example, the Astronomer. Telegram is a forum for space enthusiasts to post their findings and is being updated daily with new revelations. Miguel Alarcon and colleagues have helped to constrain the tail measurements for 3I Atlas, reporting that it extends across more than 25,000 kilometers. From this post and others, we can see some really exciting images of our new visitor. Just look at these. We have covered the brightness, rotation, and activity of the comet. But what about its surface? Well, in this respect, 3I Atlas is similar to its predecessors. Just like Oumuamua and Borisov, 3I Atlas is significantly redder than the Sun, and slightly redder than D-type asteroids like those from the outer asteroid belt. Since it is active, some of this reflected light must be coming from 3I Atlas's coma. The same was observed for Borisov, where the reflectance of the coma was drowning out the signal from the nucleus itself. We should be able to confirm this as the comet gets closer to us and new measurements can be made. For example, back in 2020, astronomers found that Borisov was producing dust at a rate of 50 kilograms per second, which helped to explain the drowned nuclear signal. Finally, the discovery of 3I Atlas has allowed astronomers to make another estimate for just how many interstellar objects there are out there. In a paper published shortly after the comet's discovery, scientists inferred a density of just 0.001 interstellar objects per cubic astronomical unit of space, that is far smaller than the previous estimates made when we discovered Oumuamua and Borisov. This density value is based on the fact that Atlas has been scanning our skies for the past 3 years and has only found one interstellar object so far. But of course, the density is liable to change and depends on many other factors. It could be that Atlas has let some objects smaller than 3I Atlas pass by undetected, or that there is a particular signal emitted by these objects that it fails to detect. We are not really sure, but estimates like these are no less useful to us, and we should try to update them whenever we are given the opportunity, so we have explored the information that we have managed to gather about this comet so far. But as we have seen, science is anything but stagnant, especially when there is a brand new toy to play with. So what are we hoping to learn from this comet in the near future? And how can we learn from our previous interstellar visitors? Luckily for astronomers studying 3I Atlas, there are 2 fairly recent case studies to draw from. We have covered both Borisov and Oumuamua before on the channel, so definitely check out our previous videos and our Oumuamua supercut if you have not already, for everything you need to know. We have already discussed some of the similarities and differences between these objects. But how can these comparisons be explained? And what do they tell us about the origins of these visitors? We have touched on one of the major differences already, and that is that 3I Atlas appears to be less active than Borisov was. 2I Borisov displayed significant cometary activity as its dust coma increased in size by around 1% per day, which indicated that it had been active for around 100 days prior to its first observations. It also had a longer tail spanning 140,000 kilometers into space. Now it could be that 3I Atlas has not been exposed to the Sun enough to begin water ice sublimation, which would raise activity levels, but Borisov entered a period of strong activity when it was still 4.5 astronomical units away from the Sun. And 3I Atlas is already closer than that, so this looks unlikely. Regardless, Oumuamua did not exhibit high activity levels either. It was a dense rocky body with noise to sublimate in the glare of the Sun, so it had no coma or tail. Astronomers are still trying to explain this lack of activity to this day, with recent hypotheses that it may have been outgassing volatiles with a low level of dust production. So it was not picked up in observations. But 3I Atlas does have a coma. So this explanation is not a one-size-fits-all for both interstellar objects. With such differing compositions and activity levels, what does this tell us about the origins of interstellar objects? Well, this is still a major subject of scientific exploration. The infamous oblong shape of Oumuamua generated a huge buzz around its origins, and theories emerged that it may be a primordial object shaped by tidal forces, or the fragment of a planetor. The aggregation of several smaller objects, Borisov, also caused speculation of its own as its composition was different from those typically seen in solar system comets. It had a higher abundance of hypervolatile carbon monoxide relative to water, suggesting that it may have formed in a carbon-rich environment. In line with this observation, it was suggested that Borisov formed in a red dwarf star system with cooler average temperatures, cool enough for carbon monoxide to condense and be incorporated into the comet. But what about the origins of 3I Atlas? Funnily enough, the velocity of the comet I mentioned earlier can be really useful here. I mentioned that 3I Atlas is traveling at a speed of 58 kilometers per second, relative to the Sun. Well, it turns out there is a relationship between the stellar age of objects and their velocity. And assuming this relationship holds true for 3I Atlas, then the comet could be between 3 and 11 billion years old. This would make 3I Atlas at least 30 times older than Oumuamua and 3 times older than Borisov, hinting at a unique and distant interstellar origin speculation. Aside, it is clear that 3I Atlas is a unique interstellar visitor worthy of our close attention, wherever it may be comparable to Borisov or Oumuamua. 3I Atlas has other characteristics that place it in a different class of object altogether. As a result, we can view this comet as an exciting opportunity for new discoveries and eagerly anticipate the scientific insights it may reveal. After all, the estimated density for interstellar objects is low, so who knows how long we may wait to be visited again. Now that we have learned a bit about 3I Atlas, it is over to you. You can keep an eye out for the comet using ground-based telescopes from around September until it disappears behind the Sun. After the October 30th perihelion, the comet will reemerge from behind the Sun in early December, ready for another round of viewing from Earth.